Okay, so here's where we're at. We have derived the differential equations that describe flow pretty much anywhere. So that's what these were. This is continuity. And then we had x and y momentum, and then we had energy. Right? And this last term is viscous dissipation. And then what we did last time is we said we're really only interested in applying these equations inside of a boundary layer. And so if we restrict ourselves to being inside of a boundary layer, a lot of these terms are not very important, right? So things change pretty slowly with respect to x, they change more quickly with respect to y, and if we just sort of followed through that kind of reasoning, we simplified them using the boundary layer simplifications to these equations here, right? And so still have the continuity equation. We have a simpler x momentum equation, and that x momentum equation includes not a partial derivative of pressure with respect to x, but an ordinary derivative, because this is how the free stream pressure varies with x. We made that change because we could basically throw away the y momentum equation as being unimportant, and that told us that the pressure gradient in the y direction is really small. And then finally, our energy equation got quite a bit simpler. First of all, we could throw away one of these conduction terms as being not very important, and of course it's the conduction term related to moving in the x direction, and we could throw away three of these velocity gradients as being less important than the most important velocity gradient, which is du dy. U is big and y is small, and that's why that's the only one that's here. So this is where we stopped, and what we're going to do next is take these boundary layer equations and make them dimensionless, right? And the reason we're going to do that is so that we can identify the meaningful non-dimensional parameters that govern the problem, right? And that'll let us understand where correlations come from, right? And by being able to understand how to represent a solution in a non-dimensional form, it's going to maximize the utility of any experiments that we might do or any CFD type simulations that we might do, so that they can be applied as broadly as possible across as many different situations and fluids and sizes and so forth as possible. So in order to find the correct dimensionless parameters, there's two ways to go, right? One way you probably learned in fluids, which is use something like the Buckingham pi theorem, where you basically select a set of dimensional parameters that are physically complete, that are dimensionally complete, so that you can then use them to non-dimensionalize all of the other parameters that govern the problem, and out of that will come a set of dimensionless numbers, right? A set of dimensionless parameters, and that's fine. It's a little bit arbitrary, though, in the sense that the resulting set of dimensionless parameters depends on sort of which three or which set of dimensional parameters you started on as your basis set. And if you don't have any other information, though, that's a good way to go. In this case, though, we do have other information, and that is these equations right here. We have these governing differential equations, and so a better way to go is to make these equations dimensionless through substitution of dimensionless velocities and positions and pressures and temperatures. And the nice thing about that is as you go through that process, what you will find is that some additional dimensionless numbers kind of pop out and arise, and you can tell based on where they come from which terms are being divided by which other terms. You can tell what their physical significance is, right? So it's not arbitrary. It's actually very focused and very specific in terms of the dimensionless numbers that you get from this process will be related to certain terms. So let's go through this process with these equations. So these are our boundary layer equations, and the substitutions that we're going to make are shown over here. So we need a dimensionless position, x and y. So to make x dimensionless or y dimensionless, we only have one length parameter to use, and that's the length of the object. So our dimensionless x position is x over L, and our dimensionless y position is y over L. And just to be clear, Any of these variables with a little squiggle over the top, that means dimensionless, right? So x squiggle is dimensionless x, y squiggle is dimensionless y. We need dimensionless velocities, u and v. So again, the only velocity that we have in the problem that we can use to make those dimensionless is the free stream velocity, u infinity. So our u squiggle will be u over u infinity, and v squiggle will be v over u infinity. We need a dimensionless temperature. So as always, you don't really want to make temperature itself dimensionless. You want to non-dimensionalize the temperature difference, and you want to normalize that temperature difference by a meaningful temperature difference in the problem. To make a temperature itself non-dimensional, an absolute temperature is always a kind of a silly thing to do, right? Because it depends on a scale, right? Celsius, Kelvin, Rankine, whatever. Making a temperature difference non-dimensional is always the right way to go. So here, I'm going to make the temperature difference between the temperature of the fluid and the temperature of the surface of the plate. So T minus Ts, I'm going to non-dimensionalize that against the free stream plate surface temperature, T infinity minus Ts, and we'll call that theta hat. So theta squiggle, I guess. So this is our dimensionless temperature T. I can get in terms of theta squiggle. And then finally, I'm going to need a dimensionless pressure. So P squiggle will be P, and we'll just normalize it by the momentum of the fluid, rho u infinity squared. So these are the substitutions I'm going to make, and I'm really just going to do algebra. I'm going to take these definitions and plug them in everywhere I need to over here and see what comes out the other side in terms of dimensionless differential equations. So let's start with the easy one, and that's the continuity equation. So here's the continuity equation. You can see in order to non-dimensionalize the continuity equation, I gotta find my pointer again here. In order to non-dimensionalize the continuity equation, I'm going to need to substitute in for u. So according to my definition, u is u squiggle times u infinity, so that's what I'll put here. V, so according to this definition, v is v squiggle times u infinity, that's what I'll put here. X is x squiggle times L, and y is y squiggle times L. So I'm just going to make those substitutions here, and this is what I get, right? U became u squiggle times u infinity, and so on and so forth. Of course, u infinity and L are both constants, so I can both pull them out in front here and here. And since the same group appears in front of both of these terms, when I divide through by u infinity over L, I get a dimensionless continuity equation that looks almost the same as my dimensional continuity equation, just that I put a little squiggle over every single term. So I didn't learn much from doing that, right? I just took this and basically put a bunch of squiggles over each term, but otherwise, not a lot of learning happened there. But you do certainly, I think, see kind of how we're going to proceed with this and sort of what the steps are. So every place I would have a du in this equation down here, or a u, you can, I hope, see that I'm just going to replace it by a du squiggle, but I have to multiply by u infinity. And here dx becomes dx squiggle, I have to multiply by L, and so on and so forth. So it becomes pretty obvious what we're doing here. So let's take the next one, which is the x momentum equation. So here's the x momentum equation. Same deal, right? I plug in for u, x, v, and y, the dimensionless u times u infinity, and so on and so forth. Over here, I have dp infinity dx. So what's that going to be? That's going to be p infinity squiggle. So that's the dimensionless free stream pressure multiplied by rho u infinity squared. This is the fluid momentum that I used to define the dimensionless pressure. And then down here, x is x squiggle times L. And then finally here I have the second derivative of u with respect to y. So that's what we did here. And if I pull all these constant terms out, I get over here rho u infinity squared times L times, these are dimensionless terms. Over here I get also rho u infinity squared times L, and then the dimensionless free stream pressure gradient. And then here I get mu times u infinity over L squared, mu times u infinity over L squared times the dimensionless second derivative of velocity. So this is an equation that's expressed in terms of dimensionless variables, but the equation itself is not dimensionless, right? Right now the equation has dimensions consistent with whatever these multiplying terms are. So if I want a dimensionless equation, I have to divide through by one of these terms. So since I guess 3 of the 4 terms have this dimension, this scaling, I'm going to divide through by rho u infinity squared over L. Right? So that's what I did here. And what you end up with is down here, right? You have a u infinity, so u squiggle, du squiggle, dx squiggle, v squiggle, du squiggle, dy squiggle. Here's my dimensionless free stream pressure gradient. And then this last term is kind of interesting because whereas these terms all just ended up being written in terms of dimensionless parameters that I already have defined, this last term is the dimensionless second derivative of velocity, yes, but multiplying it is a new set of parameters. And if I've done my algebra correctly, this group right here had better be dimensionless, right? I need to have a dimensionless equation at this point. So this group right here is a new dimensionless number that I didn't start out with, but that popped out of the process of non-dimensionalizing these equations, right? And not only that, based on where it popped out, it tells me a little bit about what it means, right? So I got this group right here by taking the viscous force, or the viscous term, and non-dimensionalizing it against the scale of the inertial or the momentum term, right? So this was the viscous term. I divided it by what was multiplying the momentum term. So whatever this ends up being ought to be related, at least proportional to the viscous term over the inertial term, right? And of course, if you do just a little bit of algebra, you can see that this group right here is 1 over the Reynolds number. So that tells you that the Reynolds number is related to inertia over viscous terms, right? Which is probably something you learned in the fluids class, right? As the Reynolds number gets larger and larger and larger, you're going to have more and more inertia relative to the viscous term. Eventually you'll go turbulent, so things like that will happen. So here's our final version of the exponential equation, written entirely in terms of dimensionless variables, right? And dimensionless variables that we had already defined. And then there's that one additional dimensionless variable, which is Reynolds number. So Reynolds number must be an important dimensionless number for this problem, which we already knew. But we also know sort of where it appears and physically what it means. So we have now the continuity equation, which gave us no new dimensionless numbers, and then the exponential equation, which gave us one new dimensionless number. And if this were a fluids class, we would stop here, but it's not. It's a heat transfer class, so we have to go down now and look at the energy equation and think about doing the same thing to that. So here's our energy equation. Let me find the pointer. Here's our energy equation. Same process that we've done now twice, I guess. Every time I have a u or an x or a v, I'm going to insert the definition of those dimensionless numbers. The only new thing is now I have a t, so I'm going to have to insert the definition of the dimensionless temperature difference, which is theta squiggle. So if I do that process, this is what I get, right? So here I had a u squiggle times u infinity. Here I have a derivative of t, so that's going to be theta squiggle times t infinity minus ts, and so on and so forth. When I get done making these substitutions, I'm just going to pull out all the parameters that are not dimensionless. So here I'm going to pull out rho c u infinity, this temperature difference in L, and that's what I have here, multiplying these two dimensionless numbers. Over here I have K times this temperature difference over L squared. So that's what I have here, multiplying the dimensionless, well, the second derivative of the dimensionless temperature. And then here I have mu times u infinity squared over L squared, right? And that's multiplying the second, well, the derivative of velocity squared. This is viscous dissipation. So just like before, this is a equation written in terms of dimensionless parameters. But it's not a dimensionless equation. If I want it to be a dimensionless equation, I have to divide through by either this term, or this term. And I've chosen to divide through by this term here, which is our advection term. And when I do that, this is what I get, right? So I've divided through by this advection term, So that leaves only dimensionless numbers over here for the advection term. But over here, I have a dimensionless group of parameters here that multiply this second derivative of temperature. And I have another dimensionless group of parameters here that multiply this velocity gradient squared, right? So I have identified here two more dimensionless parameters that must be important to my problem. And not only that, I kind of understand where they came from and what they must mean, right? This term up here where I started was conduction, and I've normalized it by advection, right? By the energy carried by the fluid. So whatever this group here is, it must be related to the magnitude of conduction to advection. And the same thing here. This term started out being viscous dissipation, and I normalized by advection. So this dimensionless group right here, it must be related somehow to viscous dissipation normalized by advection, right? So let's look at those two terms in a little bit more detail. So here I have taken this term here and brought it down here. So this is now conduction over advection. We're just going to go through a little bit of algebra to see what this term is. So obviously the temperature differences cancel out. K over rho C is alpha, right? So one of these L's cancel from the top and the bottom. So if I rewrite this, I have alpha L over U infinity. I'm going to multiply it by kinematic viscosity and divide by kinematic viscosity. And I'm left with, right here, this is the Reynolds number, and right here, this is the Prandtl number. So 1 over the Reynolds number times the Prandtl number must be related to conduction over advection, right? Sometimes this Reynolds number, Prandtl number product is referred to as the Peclet number. And that's what this really means. 1 over the Reynolds number, the Prandtl number, is an indication of how important conduction is in your problem relative to energy carried by the fluid. So let's think about a situation where conduction might be really important, right? So one situation where conduction might be really important as compared to fluid motion is the case where you have a fluid like a liquid metal that has a really small Prandtl number. In that case, this term here, 1 over the Peclet number or 1 over the Prandtl number, is going to be really, really big because the Prandtl number is going to be really, really small. The other time that can happen is in a situation where the Reynolds number is very small because the flow is very low velocity, right? So again, as that happens, as you move towards that direction, you're going to get into a situation where conduction becomes really, really important relative to advection. And you'll know when you're getting to that point when 1 over the Peclet number becomes large, or alternatively the Peclet number becomes small, right? So small Peclet numbers, large conduction, large importance of conduction. Okay, so let's then go on to this last term here and look at that a little bit more closely. So here's the last term. Get my pointer. This term must be related to viscous dissipation normalized by advection. So this is viscous dissipation over advection. And this is the dimensionless number that characterizes that, right? So again, do a little bit of algebra. So I'm going to pull out U infinity squared over C delta T. Pull that out right here. I pulled that out because that's a dimensionless number that's referred to as the Eckert number. So this is the Eckert number. And then what's left, if you do that, is what is obviously 1 over the Reynolds number. So viscous dissipation over advection is characterized by the Eckert number over the Reynolds number. And this is kind of an important thing. Have you ever used convection correlations, you probably haven't had to ever calculate an Eckert number, right? And the reason is because most of the correlations that we use implicitly make the assumption that viscous dissipation isn't very important, right? And as a result, the correlations don't even include the Eckert number. But if you're ever in a situation where this parameter, Eckert number over Reynolds number, is actually is large relative to 1, then you may be in a situation, you are in a situation where viscous dissipation is pretty important. It's as important as the advection terms, right? So this is a way for you to figure out how important viscous dissipation is for your problem. And it makes some kind of sense right? If you have a high velocity flow, then you're liable to have a lot of viscous dissipation. And actually, if you have a flow where the underlying temperature differences in the flow are pretty small, then the temperature difference associated with viscous dissipation, so with the generation of thermal energy due to viscous dissipation, might be as large as those little tiny temperature differences, right? So that's a case where T infinity minus Ts is small. In that case, you can easily get temperature differences related to viscous dissipation that are just as large. But at any rate, this is how you justify whether or not viscous dissipation is important. And this is yet another dimensionless number that must be important. So if we go now and look at sort of what we've come to, we took these equations that were dimensional, we turned them into these equations that are dimensionless, right? And in the process of doing that, we learned, I guess, three things. One thing is that Reynolds number is another dimensionless number that's important, and it characterizes at least it's proportional to the ratio of inertial forces to viscous forces. We learned that Prandtl number is another important dimensionless number, right? I guess we kind of already knew that, but now we see why, and we also see that Reynolds number times Prandtl number, also called the Peclet number, is proportional to advection divided by conduction, right? So that's how important advection is relative to conduction. And finally, in some problems, the Eckert number may be important. And the Eckert number over the Reynolds number tells you basically how important viscous dissipation is to your problems. So these equations are kind of interesting. And what we'll do in the next video is look at what these equations tell us in terms of correlating our problems, right, or correlating our solutions.